Okay. Okay, so good evening, all of you. Welcome again for one more problem solving session for the course Introduction to Semiconductor Devices, which is being conducted by Professor Naresh Kumar Emani. Just to introduce myself again, I am Soham Lakhote, currently a third year PhD student at IISc Bangalore, and my broad research area is in the design of analog and RF circuits, especially for radars that are used for vital signs monitoring. Now, for this session, the plan is I will introduce a slightly new concept which is related to what sir has taught, but that concept has a lot of importance in your future. So, when if you want to go for circuit design, RF circuit design, or analog circuit design, this concept has to be known to you at least. So, I will just quickly introduce you that concept. Then we will solve few numericals, and then we will wrap up the session. So now coming to the concept is about the cutoff and or you can say unity current gain frequency. So what this concept is actually, there are two things in the MOSFET that can limit your high speed operation. So the first thing that you can see over here is that you have a channel length L, right? Now electrons take some time to move from source region to the drain region, right? So the transit time, that is the electrons which has to cover this distance, right? So the time it takes for electrons, right? So that time corresponds to one frequency. So this is one limitation that will, what you can say, that will cause your MOSFET to not operate beyond certain frequency, right? So this is what they have also mentioned over here, that if the saturation velocity is the maximum velocity with which your electrons can travel, right? So if electrons move with this velocity and the channel length is 1 micrometer, right? So the delay comes out to be 10 picoseconds, right? So this is the formula with which you can calculate the delay, and it is nothing but your normal, what you can say, high school physics formula, right? The speed is equal to distance upon time, right? Now corresponding to this, you get a frequency of 100 giga, right? Now what they have also mentioned is that apart from this, this delays, of course, it will be there. Your MOSFET cannot operate perfectly beyond 100 gigahertz, right? But apart from that, you have resistances and capacitances, right? Now from where these resistances are coming, note that this is a N plus dope semiconductor, right? So you must have studied these concepts, what you can say, in the drift current phenomena, right? So the motion of the carriers because of the drift, right? So you must have studied what you can say, the conductivity, right? It is something like some Qn mu n times E for if the majority carriers are electrons, right? So it is looking something like that, right? Now but as you can see over here, it is again a semiconductor, though it is heavily doped, but again it's a semiconductor, right? So it will have its own resistance, this N plus region that you are seeing, right? So it will cause some resistance. Now you have the parasitic capacitances that you know, right? Your CGS is there, your CGD is there, some overlap capacitance is also going to be there. So now if I just give you a very simple circuit, right? So if you have a R and if you have a C, right? And if you apply a unit step signal, right? This is U of t, right? Now you know this is a low pass filter, right? So of course output has to reach to a final state, but it will take some time, right? And this is exponential, correct? So now the what you can say, at this t equal to 0, my input went from what you can say one value, initial value, to final value, right? Within zero amount of time. But the same cannot be happening at the output, right? So what does that mean? Is like the simple RC circuit is causing me to, what you can say, it is not allowing me to pass the changes in the input instantaneously towards the output, right? So now whenever you will get this R and C combination, whatever changes you will be having at the input, if those changes are very sudden, your MOSFET cannot react to those changes instantaneously, right? So this is what this RC circuit is telling us. Now there are many C's, there are many R's over here, right? Now because of this, you are gonna get what you can say, they will constitute their own time constants, and this will also cause a limit to your frequency of operation, right? So if this unit step is there, right? So I cannot arbitrarily operate this circuit at a huge frequency, because instead of having this kind of a instead of getting this kind of a unit step waveform at the output, I'm getting a delayed, I'm getting kind of a exponential, right? What you can say, the charging exponential, right? So this will cause some limitations on the frequency of operation. So this is what we are actually trying to, what you can say, embed into the formula. Now why unity current gain frequency? Let's say you have a MOSFET, right? This is your MOSFET, right? Now there are two things. See, first is the voltage gain and another thing is the current gain, right? Now what is the difference between our transformer and the amplifier? See, if you have a transformer, right, if you have a transformer, then if I have this kind of a ratio, right, then the V2 is equal to what? N2 by, just a minute, okay, yeah, N2 by N1 times V1, right? So even this transformer is giving me the voltage amplification, right? So why do I need this amplifier? The simple reason is because your current is also going to reduce by the same factor, right? So V2 is equal to N2 by N1 times V1, right? But at the same time, your I2 is what? N1 by N2 times I1. So the moment you multiply this terms, the product of Vi, it is gonna remain same, right? But the same cannot be said for the amplifier. Amplifier will give you the power gain. See, the basic job of the amplifier is to give you more power at the output as compared to what you have given it to the input, right? The transformer does not do that job, because transformer doesn't have power amplification. It can only give you either voltage amplification or the current amplification. That's it. So now if you consider this MOSFET, right, now the voltage gain will depend on what you are connecting at the output of this MOSFET, right, and what you are connecting at the input of the MOSFET. But if you look at the current gain, so first of all, why current gain? Because the biggest confusion that will happen is like no current flows through the gate of the MOSFET, right? This is what we had studied. There is an insulator that is present just below the gate metal layer, right? Now, but the thing is like if you keep on increasing the frequency, you have this what you can say CGS capacitance present over here, right? And what is the impedance of the capacitor? Impedance of the capacitor is nothing but 1 upon j omega c, right? So this is nothing but the impedance of the capacitor, right? So as you increase, as you keep on increasing the frequency, this impedance is gonna come down, right, as f is increased, correct? So now what happens, the gate which had such a huge impedance so that no current could have been flown at the input of the gate, now it will start seeing the low impedance and current will flow at the input, right? Now what I want, I do see some current is coming at the output also, right? That what is the MOSFET? It is a voltage controlled current source, right? You apply some gate voltage and depending on that you get a drain current, right? Now I want this functionality to be remain as it is, right? Now how I'm getting the voltage at the output? You may have some load resistor over here, right? That current, when it passes through that load resistor, it will generate the voltage over there, right? Now what I want, the current that I'm getting at the output, right, it should not happen that this impedance becomes so low that the current that is flowing at the input, let me denote it with IIP, right, and there is a current that is coming at the output, right? I don't want IIP to be greater than I output. I don't want this condition. If this happens, then that means I'm not getting any current gain out of the MOSFET, and that MOSFET is not able to give me any current gain, right? So I don't want such a MOSFET, right? So now so that's why this unity gain frequency, what you can say, the unity current gain frequency concept came about, that at what frequency my output current becomes exactly equal to the input current. This is basically what you can say a small change that you apply. So you have a DC that you apply to the MOSFET and you apply some small what you can say small voltage at the input of the MOSFET at the gate, right? So that's how the AC plus DC works. You have a bias point and on top of that you apply some signal, right? That may be that signal's frequency I'm talking about actually. So now this is the input current, this is your output current, right? So now I'm not going into the derivation of this concept. It is very well derived in the reference of Donald Niemann. So if you calculate it, then you are going to get this frequency Ft, which is called as transit frequency, cutoff frequency, or unity current gain frequency, and its expression will come out to be this, right? One assumption that has been made over here is that there is no overlap capacitance for CGD and CGS, and if it is included, the value of Ft will degrade further, right? So I just want you to remember this concept, like, and I will also explain the significance of this concept by taking some good example, by taking some current technology examples as well. So just remember this concept. I don't want my MOSFET to so that I am burning more current at the input and I am getting less current at the output. I don't want such a MOSFET, right? So there is a frequency limitation for this, and I want to operate the MOSFET. What do I mean by operate? I want to give the input frequency at the gate of the MOSFET which will be much lesser than this cutoff or transit frequency. This is the only thing that you have to remember, that my frequency that I am applying at the input for the amplification, this frequency should be much less than this ft, right? So I will just write it, f input should be much less than ft. If it is happening, then your MOSFET will be operating properly and it will be able to give you a good power gain as well, right? So I hope this concept was clear. Just for now, just remember this formula. I will after solving one sum, then I will explain you the significance of this concept. Okay, now this is just the thing that I had just mentioned, that at higher frequency the input and output impedance of the MOSFETs are dominated by the parasitic capacitances. I'm talking about gigahertz of frequencies, okay, and this gigahertz of frequency are important. So when you are doing the amplification, so what happens, you have your Wi-Fi router, right? The signals are coming onto your mobile, so their frequencies around 2.4 gigahertz is the first band and 5 gigahertz is the second band, right? So you want your circuits to actually operate at 5 gigahertz and 2.4 gigahertz, right? So at such frequencies, your parasitic capacitance start dominating. Actually they will present a lower impedance, and you cannot say that your MOSFET's input has a infinite impedance over there, right? So this is all the things that I had just told you. You can refer to this slide once I share the notes with you. Now what happens, this is what I taught about, what you can say, a normal technology nodes, greater than 180 nanometer, greater than 1 micrometer or something like that. Now what happens in the short channel MOSFETs, you know that you have a velocity saturation phenomena, right? Your current, which should have been varying as a what you can say square of the overdrive voltage, it is now just varying linearly with the with the overdrive voltage, right? So your GM, right, your GM should have been what? GM should have been proportional to VGS minus VTH, right? But the same you cannot say over here, because your ID, the square dependency is gone because of the velocity of saturation, right? The saturation velocity. So in this case the FT degrades further, and your FT in the normal case was proportional to 1 by L square, right? But FT under saturation condition, this is velocity saturation, not your MOSFET saturation, is just proportional to 1 by L. So what does that mean? Let's say I am operating at technology node of 1 micrometer, right? And I found out that my FT is very low. Maybe FT is around maybe 10 giga, and I want to design my circuit at maybe around 12 giga or something. So I cannot use 1 micrometer, right? So I have to go to lower technology nodes like 180 nanometer, 90 nanometer or something, right? So what it is telling is like, since your short channel effects start dominating now, your transit frequency will actually just vary with 1 upon L as compared to 1 upon L square. So if I had decreased my L by 3 times, right, in normal case, if I had decreased it by 3 times, I would have got 9 times improvement in my transit frequency. But under the velocity saturation condition, so it is not gonna be 9 times, it is just gonna be 3 times, right? So if you refer your curves of the FT for different channel lengths, you can just search on internet, or you can go to IEEE, and in any of the research paper you can search for the curve. You will get some idea like how the curve actually looks like. So this is what I have written: FT increases slowly for short channel MOSFETs compared to the long channel MOSFETs due to the velocity saturation effect. So what do I mean by increase slowly? When I decrease from, when I am improving my technology node from, let's say, 180 nanometer to 90 nanometer, then I had thought ki my FT will increase by 4 times, but right now it is just gonna be increased by 2 times because I have just decreased the L by the factor of 2, right? So this is the only thing that I want you guys to understand. And now we will come to the very simple problem for this. So a N-channel silicon MOSFET has the following parameters. So they have given us the mobility of electrons as 420. The oxide thickness has been given to us. The channel length has been given to us. The width is also given. The threshold voltage has also been given to us, right? And they have mentioned that the transistor is biased in the saturation region, because of course this FT concept will come mostly when you want to operate your circuit as in the amplification mode, right? So now, so that's why they are saying, okay, we are consider that we are operating in the amplifier mode, and that's why we are biasing it in the saturation region, and they are just asking to what you can say, determine the cutoff frequency, right? So now what was the formula that we had just saw? It is mu n times VGS minus VT upon 2 pi L square. See, they have not mentioned anything with respect to velocity saturation or something, and even the channel length is pretty high, right? So we generally consider above 1 micrometer the short channel effects can be ignored, right? Now let's substitute everything in this equation. So what is the value of mu n? It's 420, right? What is the value of Vgs minus Vt? 1.5 minus 0.4, right? Divided by 2 pi into what is the value of L? 1.2 into 10 to the power minus 4 square, right? So if you calculate this value, then it will come out to be around 5.106 gigahertz, right? So now you may think that okay, that MOSFET is operating pretty well at 5, but this is the maximum frequency that I can work with, right? So now just a small question to you guys: can I use this MOSFET to operate at 5 gigahertz? Can any one of you please answer whatever I have taught in the just previous 2-3 slides? Can you guys please tell me if I want to operate this MOSFET in one of the amplifiers for the Wi-Fi band, right? So can I operate it reliably or it will give me a problem?
Due to parasitic capacitance, there will be some effect.
Yeah, there is going to be due to parasitic capacitance what? You were saying something about parasitic capacitances.
Due to parasitic, there will be some noise. So we can't amplify.
Don't consider about the noise as of now. Let's imagine the signal power is reliably high, so the noise will affect you when your signal is actually very low amplitude. I'm just saying the signal will be having a good amplitude as of now. We won't be worrying about that. Don't consider about the noise as of now. Just go back to the slide. So let me go back to the slide. So just look at the slide and just tell me whether the FT we had calculated around 5.1 gigahertz, right? And I'm telling you, can we operate this MOSFET reliably at 5 gigahertz? Anybody wants to take a guess? Okay, somebody is saying yes, and the guy with which I have just interacted, he was saying no, there is going to be some problem with the parasitic capacitance, right? So I don't know whether I understood correctly or not, but we have taken the parasitic capacitance into picture, like in this equation. So the guy who was telling about the parasitic capacitance, were you talking about the contribution from the overlap capacitance or just the normal parasitic capacitance?
Normal capacitance.
Normal capacitance. Okay. So see that because of you are seeing over here, right? CG is there, right? So the gate capacitance, or what you can say, the effective gate capacitance that is present at the MOSFET's gate, it has been taken into the account, and this is the main limitation. This RC that I told you, right? So this capacitance is the main culprit which is actually causing the low impedance at the gate of the MOSFET, which should have been infinite, right? Because it's I'm seeing just a insulator from the gate, right? So the input impedance should have been infinite, but this capacitance itself is causing the problem. So just what I have told you, the input frequency should be much lesser than the FT to operate your MOSFET reliably for a given frequency of for the given input frequency, right? So now why we do this? Because of course you want some current gain out of this MOSFET, right? You don't want to operate this just like a transformer, because this MOSFET has to give you a power gain and good power gain, right? This is the main difference between the amplifiers and the transformers, right? So I am just very close. Actually, if you look, then 5 gigahertz and 5.1 gigahertz are very close, right? So I won't be able to operate it reliably, and I won't be able to extract maximum performance out of the MOSFET. So it will be better if I just decrease my technology node from 1.2 micro to maybe what you can say, at least I need to reduce it by the factor of at least 1 by 2 or 1 by 3, so that I can say okay, I am operating well behind my FT and my MOSFET will give me a good power gain. So that's what I will say, no, we cannot do it. You need to take a little bit advanced technology for this type of example. Now coming to the significance of this FT and how it affects, right? So there will be two case studies that I will be taking. First is for the 5G, and the second is for the automotive radar. So you guys must be having cars at your home, right? So you must be seeing that there are radars that are attached, and when you take reverse, like when you try to take when you are trying to park and when you are trying to take your cars in the reverse mode, screen appears in front of you, right? And there is already what you can say some kind of not like this. Just a minute. Yeah, so some kind of this kind of figure appears on top of your screen over there, right? So now this figures, whatever you are seeing, you are able to see it just because there is a radar that is present in your car actually. So it is actually telling you, it is actually doing all the imaging for you, and by doing some signal processing, this type of figure is actually appearing on your screen, and on screen you are also able to see what is behind your back, right? So this type of a rectangle which says, okay, don't go near this region or else you will be very close to the behind vehicle, right? So all this is done because there is a radar that is doing the imaging for you over there, right? Now coming to the case study of 5G, see there are this is taken from the reference from the Qualcomm actually. So there are three bands, right? One is the below 1 GHz, one is between 1 to 6 GHz, and another is above 24 GHz. This is the millimeter wave band, right? So now why this concept of FT was important to you? Because the circuit that I have designed, let's say in these two bands, right? So let's take the case of like for our group, right? Our research group actively designs the radar for like which are working till 5 GHz, right? We generally use 180 nanometer technology now, right? And it suffices. It does a very good job if you want to design the circuits over here. But if you tell me now you guys answer me. If I try to use the same 180 nanometer technology node for designing the 24 GHz circuit according to the FT, will it work properly or I will get some problem over there? Can you guys please tell me now? This should be easy.
You will have a problem.
We will have problem, right? Exactly. Good. So we are gonna have problem over there. So that's why if you open any papers or if you open any products of 5G, let's say the Qualcomm makes a lot of radio frequency circuits, right? They make a lot of ICs over there. So if you see any IC like which is operating above 24 GHz, you will not see 180 nanometer technology over there. They will be designing the circuits in 45 nanometer, 28 nanometer, or maybe even 65 nanometer will suffice for 24 GHz, but I will still suggest this is very tricky. It is not that easy to design such a high frequency circuit in 65 nanometer. You will face some problems. So generally they design the circuits maybe in around this technology node. So if you go to their products and they will be mentioning the technology node and all, so just go to their website and just try to check at what technology node they are designing this millimeter wave circuits. Now you will get an understanding why they are not designing circuits at 180 nanometer technology, why they are moving to lower technologies actually. So this FT is one of the primary reason, because these RF circuits you want to get a good amplification also over there, right? They should not just act as a transformer. You want a good power gain out of your MOSFETs, right? So you have to operate at a much lesser technology node, so that your FT is much higher as compared to this 24 GHz, right? Now the second example that I want to give you is about the case of the automotive radar. This is taken from the Semiconductor's website, and by the way, just a standard disclaimer, I am not endorsing the products of these companies. I am just taking it for an educational purpose, okay? So don't tell me that we are favoring these two companies. So now coming to over here, so this is automotive radar. So it's a imaging radar. You can say that that is able to measure the distance between different cars that are. So for example, your car is here. There is one more car here, one more car here, one more car here, one more car here, right? So if this car comes very close to your car, right, your car sounds a bit over there, right? So that beep is coming because the radar is capable of detecting, okay, some target has come very close to your car, so please move your car somewhere, because the distance is, what I can say, lesser than the safety distance that is supposed to be there, right? Now coming over here, again it is saying our solution encompasses a state-of-the-art radar in TSMC 28 nanometer CMOS, right? And now why 28 nanometer CMOS? You will be able to see this is the radar IC, right? That person is holding in the hand. This is operating in 76 to 81 gigahertz of frequency band. So this is a very high frequency even as compared to your 5G frequency. The 5G frequency was what around? It was around 24 gigahertz, right? This is almost what you can say more than triple of that. So you need a lot higher FT over here as compared to for the circuits which you were designing for the 5G, right? So now again you must have got an understanding ki why they are designing the ICs in 28 nanometer CMOS technology and why they are not working in 180 nanometer technology or maybe 360 nanometer technology, right? So this is just the example that I wanted to give you, how your concepts that you are actually understanding right now, how they are actually being implemented practically by the designers all over the world. So this is just a feeling that I wanted to give you, and I hope this was clear to you. Now the concept of transient frequency is over. So we will move on to some good numericals. So now in this numerical, so let's say what they are asking. Consider an ideal N-channel MOSFET with a width to length ratio of 10. Electron mobility has been given, oxide thickness has also been given, and the threshold voltage has also been given, right? Now what they are asking, determine the maximum value of the source resistance so that the saturation transconductance is reduced by no more than 20% from its ideal value when VGS is equal to 5 volts. So it may be a little bit difficult to understand what they are asking. I will just simplify it for you. So this was your MOSFET, right? This is gate, this is drain, this is source, right? Now again I have one more MOSFET, right? Just a minute. Yeah, you have a drain, you have a gate, and you have a source over here, right? But the only issue over here is that you have a source resistance that is present over here, and let me name this terminal as S dash. So if you look at the circle that I am drawing, right, these two are exactly same, but the problem is that I cannot separate out the source resistance. That is, if you ask me, can I give the input, this is first MOSFET, this is second MOSFET, right? Now can I give the input at S instead of S dash in the second MOSFET? Then the answer is clear no, because this resistance is coming from the N plus region that is there at the source side, right? I just told you, right, there is a resistance over there in the drain and the source region, right? So we cannot separate out this resistance, and whatever input I have to apply at the node S dash, right? This is the only thing that they are saying. So what they are asking, so first of all tell me, the GM is what? GM is, you know, directly proportional to what? VGS minus VTH, right? Now I just want to ask you one question. So what is the direction of current flow? The current flows like this, right? So now this VGS, the ID is proportional to what? VGS minus VTH whole square. Now that VGS, what I was saying is half mu n Cox W by L times VGS minus VTH the whole square, right? This VGS that you are seeing over here, it is the VGS of this MOSFET. MOSFET doesn't care what resistances are present outside. It just wants that whatever source voltage and gate voltage you will apply to me, I will give you this much current, right? So this VGS is nothing but the GS, this GS that I am saying. This GS dash is not what you will be putting over here, okay? So now, so I hope the question is clear to you. Now what I am asking, so I will ask you one question. So can you tell me in which case the VGS which will be applied across the MOSFET will be higher, in case of the case number first or in case of the case number second? The current is flowing like this. You have a resistor over here. You are applying the voltage. You are applying maybe the same voltage at S dash and S, right? So whatever voltage you will be applying, it will be going directly to the source terminal. Whatever source voltage you will be applying, it will be there will be something that will be happening over here, and some voltage will come over here, right? Now I am asking you, in which case the MOSFET will be getting a larger VGS, in the case number first or in the case number second? Yeah, correct, exactly. So in the case number first, so why Pythagoras said like that? Because if you take a relation between Vs dash and Vs, right? So what is Vs? Vs will be nothing but your Vs dash, right, plus ID times Rs. Correct? This quantity is what you can say is positive. Even this is positive. That means the source voltage that will be applied at the source of the MOSFET it is going to be higher, right? If this source voltage is going to be higher, then the VGS value is gonna be less, right? Because what is your VGS? VGS will be nothing but VG minus VS, correct? So if this quantity increases, then my VGS has decreased, right? And if my VGS has decreased by maintaining all other terms as constant, then your GM, which is directly proportional to this term, is going to be lesser for second case in terms of in comparison with the first case, right? So now what they are asking in the question is like, let's say this is the GM for this new over here. Let's say this is GM new, and over here this is GM old, right? So now first of all, for solving this question, we have to find the relation between the GM new and GM old, so that we can actually equate, like what we will be equating. We are just telling that the GM new will be 20% lesser than the GM old, and I just explained you the reason why the GM for the second case is going to be lesser, right? So now I hope the question is clear to you. Now let's try to approach the question now. So what will be the VGS? VGS will be nothing but VGS dash, right, minus IDRS, right? So let me denote this as equation number 1 over here, right? Now coming to how are we going to solve this question. So first let's go with a very fundamental. What will be the GM old, right? Dou ID, right, by dou VGS, right? This is my GM old, right? Now I want to find the same expression for the GM new as well, right? Now the only thing that you must be noting over here, this GM old, what it tells you, if I have what you can say signal applying at the gate, right? So if I have a small change in my signal that I am applying at the gate, then how much change I am getting in the current, right? So the change applied at the input of the, that is between the gate and source over here, right? Now I have just told you, you cannot apply the signal at the source node. You have to apply the signal at the S dash node for the second case, right? So now the GM definition will be what? Of course you will be having your ID, right? Now you have to differentiate it with respect to GS dash. You cannot differentiate it with respect to GS, because you are applying the input between the gate and S dash, not between the gate and source. I hope this concept was clear to you, because this is one of the main concepts of this question, and if it is not clear, then it will cause a havoc in, it will cause a confusion of what I am doing. So please note down these things that I am writing over here. This may be, I will write it as equation number maybe A, and I will write it as equation number B. Okay. So now what is dou ID by dou VGS? This is just a simple formula that we know, right? So GM old, right? It is what? Mu and Cox W by L, right? Times what? VGS minus VTS. Okay. Now what will be? Let's say this is my equation number 2, right? Now coming to the GM new, right? So now how am I going to do it? Is like, okay, let me do it over here itself. So I have ID equation with me, right? Now dou ID by dou VGS dash, right? Just look at this equation. I'm referring to this equation, okay? This equation. So now what I'm going to do, I am gonna just differentiate it, right? So what it will be? Mu n Cox W by L times what? VGS minus VTH, right? Now I have to carefully check, right? See, I'm differentiating with respect to dou VGS dash, but there is VGS present, and I have a relation between VGS and VGS dash, right? So I have to take the derivative of this bracket itself, right? So what it will be? VTH will not vary with VGS dash, right? So it will be what? Dou VGS divided by dou VGS dash, correct? And how am I going to get this term? By differentiating this equation over here, right? So now let's calculate this term over here, right? So what will be my dou VGS by dou VGS dash? What it will be? It will be nothing but 1. I am differentiating this equation. 1 minus dou ID by dou VGS dash, right, times RS, correct? Now what is this term? what is this term? I have already defined this term in the equation number B, right? This is the term that I was referring to, right? So what will be this? This will be equal to 1 minus gm of nu, right, into rs, correct? So again I will note it down. I will note down this as equation number 3 maybe. No, not 3. This should be 3 and this should be 4. Right? So now let's substitute it over here. So equation number 3, if you look over here, this rho id by rho vgs, right? Again it's a gm nu. This is what gm nu, right? So I will write it in the bottom. Gm nu will be what? This mu and Cox w by vgs minus vth is what? This is your equation number 2. This is your gm old actually, right? So just a minute. Yeah. So your gm old, right, into dou vgs by dou vgs dash. So this is, we have just calculated 1 minus what? Gm nu times rs, right? So this is my equation number 5, right? So please note down this equation. We will be using this for solving the question. Now I will be just rearranging this equation because we have got the relation between the older GM and the newer GM, right? So I am just rewriting the equation number 5 in the next slide. Okay. So what will be the value of GMU? Your GMU, if you rearrange, it will come out to be GM old, right, divided by 1 plus GM old times RS, right? Now you know I am a big fan of doing the sanity check, right? So let's apply a sanity check. So what sanity check I am going to apply? You guys told me that your VGS will be lesser for second MOSFET, and on basis of that concept, I told you that the GM, the new GM that you will be getting, it will be lesser than your older GM, right? This is the sanity check that we have to apply, right? So I told you the GMU should be lesser than GM old, and you can clearly see over here the GM old is divided by this 1 plus 2 over here, right? So this thing, let's say even if it is smaller, your GMU is going to be lesser as compared to your older GM value, right? So if it is lesser, then the sanity check confirms what we had done theoretically. So this formula is looking like a correct formula, right? Now let's go back to the question and let's look at the part number A that they are asking. Determine the maximum value of source resistance so that the saturation transconductance, right, this is the new transconductance they are talking about, is reduced by no more than 20% from its ideal value, right? So what was the ideal value? This was your ideal value, right? Correct? And this is your new value that they are talking about. So what they are asking me, what they have given me is that GMU is, right, it is what, 80% of GM old. Correct? So now this will be how much? 4 by 5 times of GM old, right? This is the GMU that they have given. So I will just write it. This has been given to me. So let's put it in the formula, right? So what this will be becoming what? 4 by 5 times of GM old is equal to what? GM old upon 1 plus GM old into RS. So GM old and GM old will be getting cancelled, right? So GM old times RS will be nothing but 5 by 4 minus 1, which will come out to be 1 by 4, right? So now the source resistance that they were asking in the question, it will come out to be 1 by 4 times of GM old. So my job is to find this GM old, right? And do I know the formula for GM old? Of course I know the formula, right? So what is the formula for GM old? It's nothing but what? Mu and Cox W by L times VGS minus VTH, right? Now let's check whether they have given me enough data to find the question. So first of all, they have given me that VGS is 5 volt. They have also given me that VT is around 0.65 volt. So they have given me the data to calculate VGS minus VTH, right? Now coming to the Cox part, mu and times Cox, right? So they have not given me the Cox, but they have given me the Tox, right? And the Cox can be found out by doing epsilon ox by Tox. And they have also given me the mobility, right? So now let's calculate the Cox first because this term is unknown to us. So what will be Cox? Cox is nothing but epsilon ox by Tox, right? what is the epsilon of oxide? It's nothing but the 3.9 into the permittivity of free space, right? Into 10 to the power minus 14, right? And you have to divide it by the thickness of oxide. So thickness of oxide is given as 475 angstroms. So 475, right, into 10 to the power minus 10. This is coming in the meters. Now I have to multiply it by 100 to convert it into centimeter, right? So if you calculate this value, then the Cox value will come out to be what? 7.266 into 10 to the power minus 8, right? So it will be in the farads per centimeter square, right? Now everything has been given to me. Now Vgs minus Vth I know, W by L I know, mu also I know, right? So now let's calculate, substitute everything in the formula of Gm old, right? So what is the mu n? Mu n they have given as 400. Cox I have just calculated over here, correct? Now coming to the W by L ratio, W by L ratio they have given as 10 in the question, right? So it is 10 into Vgs minus Vth. Vgs they have given is I guess 5 volts, right? 5 and the Vt is 0.65. So 5 minus 0.65, right? So if we calculate this value, then the Gm old will come out to be around 1.264 into 10 to the power minus 3 Siemens. So this is the value of Gm old that I have calculated. Now we will substitute it, right, in this. So substituting, then your Rs will come out to be around 1 upon 4 into 1.264 into 10 to the power minus 3. So your Rs value is going to come out around 197.73 ohms. So this is the value of Rs that they were asking. Like what will should be your source resistance so that your new Gm will not be dropping by more than 20%. So I hope this part was clear. If you guys have any doubts, then please ask, because this was an important question. And coming to the second part, they are asking is okay, using the value of Rs calculated in part A, how much is Gm, the new Gm, reduced from its ideal value when Vgs is equal to 3 volts, right? So now let's try to digest this. So they are asking, okay, now this time we are giving you the source resistance value that we had just calculated, right? So now using this source resistance value, now they have just changed the Vgs over here. See, for older case they have given the Vgs as 5 volts, right? Over here they are telling now your Vgs is dropped to 3 volts, right? So now what we have to do, the older Gm that we have calculated, right? That old Gm was calculated for Vgs equal to 5 volts, right? Now we have to calculate the same old Gm for Vgs is equal to 3 volts, right? Now this Gm, like the old Gm that you have, now this Gm will become your Gm old over here, and the Rs value has been given to us, which we have calculated from the previous question, right? So Gm old is given, Rs is given. Now my only job is to find the new Gm value, right? So again it's based on the same formula, right? So I will be using the same concept now. So now let's calculate the Gm old, right, at new value of Vgs, that is 3 volts, which they have given to us, right? So this will be what? Mu n Cox of W by L into Vgs minus Vth, right? We have already calculated everything. This is 400. Then the Cox that we have is around what? 7.266 into 10 to the power minus 8. The W by L has been given to 10, and the Vgs now they have given us 3 volts, right? And our Vth is as it is. So now your Gm old, correct, at Vgs is equal to 3 volts. Now this will come out to be 6.83 into 10 to the power minus 4, right? Siemens. Now you know again I am a big fan of sanity checks, right? So now this Gm value is lesser as compared to what I had got over here. See, compare this value. This is what 1.2 into 10 to the power minus 3, right? And this value is what 6.83 into 10 to the power minus 4. So this value is lesser, and it makes sense because your Vgs that you are applying, the 3 volt was is lesser, because in the previous case you are applying 5 volts of Vgs. Over here you are applying just 3 volts, right? So your Gm should reduce, right? So this is looking fine to us by doing the sanity check, right? Now let's substitute everything into the formula, right? Gmu is what? Your Gm old upon 1 plus GM old times RS, right? So let's substitute everything. 6.83 into 10 to the power minus 4, right? Upon 1 plus 6.83 into 10 to the power minus 4, right? Into your RS. RS was around how much? So I guess 197.7 ohms, right? So your new GM value, right? It will come out to be around 6.017 into 10 to the power minus 4, right? So this is your new GM value and this is your old GM value, right? So if you want to calculate the percentage change, then it will be nothing but what? 1 minus 6.017 into 10 to the power minus 4 upon 6.83 into 10 to the power minus 4, and this will be multiplied by 100, right? So now this percentage change will come out to be around 11.9%. Okay, so guys, this was the end of the question. Do you guys have any doubts? I will proceed with the next question. This was a little bit tricky question, not a lot tricky, but the initial concept was important. So yeah, I will be moving to the next question, and this will be, I guess, the last question for today. So now let's see what they have given. So the parameters of a silicon MOSFET are the acceptor and concentration is given, the threshold voltage has been given to us, and the that what you can say the transconductance, that Kn dash parameter, the process parameter has been also given to us. The width has been given, and the length has been given to us, right? So now they are asking determine the current ID dash at VGS is equal to 1 volt, right? For VDS is equal to 2 volts and for VDS is equal to 4 volts, right? So now I just wanted to ask you guys, have you guys solved this such type of questions in the previous problem solving session? If you have solved this, then I will be moving to the next question, because the next question is a little bit new question and that will help you. It's a numerical based on the concept of the DIBL. So I just want a confirmation from you guys whether you have solved this type of a question in the previous session or not.
So just substituting the values, right?
Yeah, you're just substituting the values, and the only new part is they are just asking you to calculate the output resistance over there. So this output impedance, you know that this is what 1 upon lambda ID, right? And you also know the relation, right? Your lambda times VDS is what? Lambda times VDS is what? Delta L by L, right? So you know you calculate the delta L first using this formula, and then you calculate the lambda, and the moment you calculate the lambda, you get the output impedance over here. Right? So this is the only additional concept that is there. So you guys are familiar with just substituting the values over here, right?
Yes, sir. You can proceed, sir. Then.
Okay, so okay, no issue. So what I will do is, like, when I will be giving you the notes, the session notes, right? When I upload the video, so in the notes I will just solve this question quickly so that you guys can refer, and if you guys have any doubts, then you can come back to me in the next session. Okay. So now coming to the next question. So yeah, it's a very interesting question. So what they are asking, calculate the theoretical punch through voltage assuming the abrupt junction approximation. So what the hell is this? Okay, so now this is n plus, right? And this is your P substrate. I'm just drawing a rough diagram of the MOSFET, and you know there is a depletion region that is present around here, right? Correct. And what you can say, let's say you have oxide, right? And you have a gate over here, right? So now this is your source terminal and this is your drain terminal, right? So now you guys must have been taught about the DIBL, the concept of drain induced barrier lowering, right? So now what happens is, like, I'm just drawing the junctions and their depletion region, right? So this is your N plus, and again this is your N plus, right? And you have a depletion region, right? So since in the older technology nodes, right, since this source and drain junctions were separated far apart, like, there was no chance that the depletion region in the drain side is gonna affect the depletion region on the source side. Like, there is not so much interaction between the depletion regions that are present on the drain as well as the source side, right? But you know, like, as we are moving to the higher technology nodes, that is, we are reducing the channel length continuously, right? So these source and drains are being brought to closer and closer and closer. Now what is happening over here is, like, since they are becoming closer now, and you are applying the VD over here. This is your VDS, right? And this is a positive voltage. See, this is the N plus this is the N plus side. This is the P substrate side. You are applying a positive voltage on the side of N region, right? So that means you are making this PN junction more and more reverse bias, right? So as you apply higher and higher value of the VD, your depletion region will keep on increasing, and it will reach a point where it will touch the depletion region on the source side. Now why the depletion region on the source side is not increasing? Because this substrate is grounded, right? Your source is also grounded. The only thing that is increasing is your drain voltage. So let me write it over here. So your VDS is positive. You are not even touching the source voltage. So that's why the depletion region over here will remain constant. The only thing that is going to increase is the length of the depletion region that is occurring because of the PN junction that is present at the drain side, right? So now what is the punch through? So the punch through is more what you can say a more critical, not more critical, it is the some phenomena within the DIBL. So you know the DIBL, right? So the depletion region start increasing and the potential barrier gets lowered, right? Now when you keep on increasing the drain voltage further and further and further, this depletion region actually touches the depletion region over here, and what happens is the channel length that you have, right? So let me denote the length of the depletion region by X dip of D, and let me denote the length of the depletion region by X dip of S, right? So now what happens at the punch through exactly is that your L channel length is there, right? It becomes exactly equal to X depletion of D plus X depletion of S. That is the depletion regions of the drain touches the source depletion region, and the total length of the both the depletion region is equal to what? Your L channel, right? Now what they are asking is ki please calculate the voltage at the drain such that this condition occurs. Now I just told you we are applying a VDS over here, right? So now they are asking, okay, see, your depletion region is there, right? And you know, for the reverse bias case, you know the formula, right? What is the depletion region? What is the width of the depletion region when I apply a particular reverse bias across the PN junction, right? So now what they are asking in the question is like, please use that formula for both these cases, for both the width of the depletion on the source side and the drain side, and please let us know what is the reverse bias voltage that you are applying at the drain side such that the summation of both the depletion widths is come out to be L channel, which is by definition the definition of the punch through. Okay, so I hope the concept was clear to you. Now this was the first thing that we got from the definition of the punch through, right? Now let's write the formula, right? The depletion width with respect to the voltage that we apply, right? So from the PN junction, you know this is your formula, right? Q times Na into what? VBI plus VR. I hope you guys remember this formula. Don't forget this formula. This is a very important. Now coming to the everything, epsilon is known, Na is known. Reverse bias we have to find, right? For what? For depletion, for the depletion on the drain side, the reverse bias is not applied for the source because the substrate is grounded and the source is also grounded, right? So now we don't know the value of VBI, right? So let's check whether they have given us the, well, let's write the formula for VBI first. It will be helpful. So it is what? KT by Q ln of NA upon Ni square, right? So this is the formula, right? Now let's check the value of Na and Nd. So the I just want you guys to understand is like the source and the drain regions are N plus doped, right? So you will be getting the Nd over here, and the Na will be your what you can say the doping, that is a P substrate doping that is happening, which is given as 10 to the power 16, and a channel region doping of 10 to the power 16, right? So using these two values we will calculate the VBI. So this will be nothing but 0.0259 times ln of what? 10 to the power 16 into 10 to the power 19 divided by 1.5 into 10 to the power 10 the whole square. So if you calculate this value, then you are going to get around 0.874 volts. So this is the value of VBI that you have, right? Now coming to the for source side, right? Why I'm checking at source side? Because I don't have to apply any bias over there. So let's quickly calculate the X depletion at the source side. So for this case, VR is our 0. VR is 0, right? I'm gonna use the same formula. Look at the formula number here. I will be using the same formula over here by just substituting VR at 0, right? So 2 into epsilon SI is what? 11.7 into 8.85 into 10 to the power minus 14, right? Divided by 1.6 into 10 to the power minus 19 into the value of Na has been given as what? 10 to the power 16, correct? And the value of VBI we have calculated over here, 0.874, right? So the depletion region on the source side, its width will come out to be around 0.336 micrometers, right? So now let's denote it as equation number 2. And now similarly we will do for the what you can say, no, we will not do the same. What we will do is we will substitute from 1 and 2, from 1 comma 2. The channel length has been given to me, right? It's 1.2 micro. 1.2 micro will be what? 0.336 micro plus the depletion region width that will be coming from the drain side, right? So now if you just substitute, then what you are gonna get is like the depletion region width on the drain side, it is gonna come out to be 0.864 micrometer, right? So this is what we wanted. Why we wanted this? Because we want to calculate the VR for drain side. We know everything, we just wanted the depletion region width at the drain region. Once we know that, then we know how much reverse bias we have to apply over there, right? So now let's use just a minute. Okay, I don't have any more slides. Okay, I'll just make a space over here. End of question. Okay, I'm just solving the previous question on this slide. So that's why I've written end of question. I forgot to insert one more slide over there. So now what we know is like X depletion at the drain side is what? 0.864 micro, right? So now this 0.864 micrometer is gonna what? Root of 2 epsilon SI, that the same thing that I am writing, right? 8.85 into 10 to the power minus 14, right, upon 1.6 into 10 to the power minus 19 into 10 to the power 16, correct, into VBI. What is the VBI? 0.874 plus VR, right? And this VR is nothing but my VDS that I am applying, because VDS is the reverse bias voltage for that particular PN junction, right? So if you square on both the sides and if you solve for the value of VR, then the VDS value that you are gonna get is around 4.8935 volts. So this is the voltage. This 4.8935 volts is the voltage that you were supposed to apply so that your punch through occurs and your source and the drain depletion regions will just touch each other. So this is just a numerical that was based on the concept of the DRL. So that's why I thought it's important to take this numerical. Guys, this was the last question for today. If you guys have any doubts in any of the questions or any concepts or of the FT, unity, current gain, frequency, then please feel free to ask. I'm stopping over here.
So GM calculation, why did we?
In the GM calculation, can you repeat what you were saying?
Before previous question, we didn't consider body effect, right? GMB. Why it's not the case?
GMB, you can, in this question, what you can do is you can see they have not given us the body voltage over here, right? We have to apply some bias at the body voltage, right? So the substrate that you are seeing, you have to if you are not applying any bias at the body voltage, then you always assume that what happened, just a minute, yeah. So your VSB is 0 in this question. So what you can do is like whenever they have not mentioned anything about the body effect, right? So you can always ignore it. Are you able to see my slides, or you are seeing some black window?
You can see it visible.
Yeah, you can see, right? So since the body voltage was not given and they had not mentioned anything about the the body voltage or body effect, so we can always ignore this in the question if it has not been mentioned specifically.
Right, sir?
Yeah, correct. Guys, any more questions? That concept was of cutoff frequency was clear, right? Or do you guys have any doubts over there? please feel free to ask, because I'm from a circuit design background, so we heavily use that FT. I mean, not heavily, I mean, we decide the technology node. So, for example, if you go to any industry, let's say after your graduation, and if you join over there, then you should be knowing why you are using that particular technology node. It should not happen that you are doing RF designing for the radar or for 5G, and you are asking questions like why we are using such a lesser technology node. So the concept should be clear. So if you guys have any doubts over there, then just please ask me. I will be happy to answer any questions. No doubts. Any doubt in any of the questions, any of the concepts that we have discussed today, the problems that we have solved, this will be the last chance for you to ask the doubts, or else we will close the session.
No doubts, sir.
No doubts. Okay. Thank you guys for joining for one more session, and sorry for ruining your another Sunday evening. Please enjoy the rest of your day, and hope to see you in the next session. Have a good day. Thank you guys.
Sir, will you cover Zener voltage regulator, sir?
Zener voltage regulator.
In
No,
next session.
I don't know whether sir is gonna cover or not. I have to look. Like it's mostly a circuit part, right? So the electronic circuit analysis or analog circuits one generally takes care of the Zener diode, and also I don't know whether he will be covering or not. I literally don't have any idea.
No, sir. Will you cover in next session, in upcoming sessions?
The Zener diode. I have to
Yes,
look
sir.
what has been taught, because in the next week's contents it is gonna be about the optical generation and all. I guess he's gonna cover photodiodes and yeah, correct. So I have to, according to their policy, I have to cover only that week's contents. Like whatever content is related to that, I have to take the numericals from that only, because taking the numericals from the Zener diode, that too in the semiconductor course, it's not gonna, what you can say, a suitable thing to do. And if other people complain, then I will be screwed up. Okay.
Okay, sir. Okay. Thank you,
Yeah,
sir.
if you guys, if you want, then I can send you some references and numericals. That's the only thing that I can, maximum I can do. Yeah. Okay. Yeah. Sure. Yeah. Thank you guys. We will close the session now. Have a great day, guys. Thank you.